Alright, so let's cover the material. If you don't like that, you can stay after school on the last Tuesday and just do test 5 in your midterm right then and there.
I like that idea.
You like that idea? That was a joke. That would be a lot to do right after you covered new material, before you even did the homework. Because you'd be covering new material, and then at the end of the day, being tested on the material, plus your new material. It'd be very cramped-packed. In other words, there's no good way to do it. So, we're going to do it the best, worst way we can. The best, bad way we can. I don't keep my laptop. Just get started. Okay, what did we cover last week? Last week we covered proof using contrapositive and proof by contradiction, right? You remember what both those were?
Yeah.
What's contrapositive of A implies B?
Not A implies not A.
Wonderful. And then contradiction was we showed, so we were trying to show A implies B. We showed A and not B is impossible. Therefore, if you assume A, you're going to have A and B, and this is going to be true. We showed that A and not B is impossible or implies something false. This was logically equivalent to this, right? Remember this?
Yeah.
Okay. So, we're going to be extending on proof by contradiction. We're going to be doing a special proof by contradiction, and it is proof by smallest counterexample. So how does this work in general? You have some assertion about numbers. You say, assume by way of contradiction that the assertion is false. If the assertion is false, then there has to be one number for which it's false, right? If I say it's false that every prime number is odd, then there has to be at least one prime number that's not odd, right? So if I say an assertion about all the natural numbers is false, there has to be at least one natural number that makes the assertion false. That's what it means for the assertion to be false about all naturals. If we have for all x some statement about x, and we're talking about the negation of that, that means there exists an x such that not the statement about x. That's what we do. We say, if we have a statement like this, we say assume by way of contradiction this, right? You with me so far? Okay, so we're going to say, assume by way of contradiction that there is some x that makes a statement false. Furthermore, we're going to say that there's a smallest x that makes the statement false, and work with that smallest x, the smallest number that makes the statement false. So that's high level what we're thinking when we're thinking proof by smallest counterexample. We're going to say, assume by way of contradiction that there is an example that makes it false. Furthermore, I want the smallest example that makes it false. And we're going to work with that smallest example. So to get a smallest example, we need what's called the well-ordering principle. This is not something that first let's go over what it is. It should be very intuitive. Well-ordering principle. Every non-empty set of natural numbers contains the least element. If I have a set of natural numbers, there's a smallest thing in there. You can't give me a set of natural numbers that doesn't have a smallest element. Non-empty set of natural numbers. You understand what I mean? What's a set of natural numbers? All the evens. The set of all x such that the set of all x in n, all the natural numbers, such that 2 divides x. Okay, there's a set of natural numbers. Does it have a least element?
Yeah.
What?
2.
0. 0 is the smallest even natural number. Every set of natural numbers has the smallest element.
0 is an even number.
0 is even. Does 2 divide 0? Yes. 2 times an integer equals 0? Yes. What integer? 0. 2 times 0 equals 0.
0 is even?
Yes, 0 is even. I've had this conversation so many times with students, it's tiring. 0 is an even number. 2 times 0 equals 0. Therefore, 0 is even. What does it mean to be even? It means to be divisible by 2. What does it mean for a number to be divisible by 2? It means 2 times some integer gives you that number. 2 times 0 gives you 0. 0 is even. Okay. Anyways, every non-empty set of natural numbers contains a least element. and we're not going to be proving this in this class because as a general rule, this would be an axiom on your natural numbers, or you would have an axiom that you could derive this from. So in calculus, we have the completeness axiom, which we use to show that every bounded from below subset of integers has a least element. But similar thinking here. So every set of natural numbers has a least element. It's not something we're proving in this class, it's something we're assuming because in some developments math, this would just be an axiom, not something that you prove. With me so far? You understand what it says? Because you're going to use this a ton. Ready? Let's go. Okay, so we're going to do a proof using this well-ordering principle. And this is a proof by smallest counterexample, and here's how they generally work. So I'm going to prove that every natural number is even or odd. Very, very, very important. I need to be talking about natural numbers because the well-ordered principle only applies to natural numbers. Is it true that every subset of integers has a least element?
No.
No. Is it true that every subset of rationals has a least element?
No.
No. Is this making sense what I'm saying, or is someone confused? You with me? Okay. So when you do proofs that use the well-ordering principle, you have to be talking about the natural numbers. Okay? That's what the well-ordering principle applies to, just naturals. So every natural number is even or odd. We're going to do a proof of this. We're going to do a proof by contradiction. So I'm going to, first I set up the set, and you'll see where I set my contradiction here. So I'm going to say let x be the set of all natural numbers that are not even and not odd. Right? So we said we're proving every natural number is even or odd. I'm saying let x be the set of all natural numbers that are not even and are not odd. Question, how many things are in x?
None.
None. Every natural number is even or odd. X is empty. I said x is a set of all natural numbers that are not even and not odd. We know in our heads x is empty. Assume by way of contradiction that x is not empty. You with me? You understand how we're doing an assume by way of contradiction of this statement up here using this set x? So x is a set of all things that make this false. We know that nothing makes this false, so x should be empty. We're going to assume by way of contradiction that x is not empty. Okay. Well, notice, by the way x is defined, it's a subset of natural numbers. How do I know that? Oh, because I didn't write it right. So x is equal to the set of all n in n, all natural numbers, such that n is not even and n is not odd. Sorry. So x is a subset of natural numbers. You with me? So by the we just really assume by way of contradiction that x is not empty. Since we assume x is not empty, then by the well-ordering principle, x has to have a least element. We'll call it little x. So what is little x? It is the smallest natural number that is not even and not odd. We know little x doesn't exist. We assume by way of contradiction that you could get such a little x. You with me so far? Since 0 is even, then we know x has to be greater than 0. X is the smallest natural number that's not even or odd. 0 is even, so x can't be 0. So x has to be greater than 0 because it's a natural number. You with me so far?
Yeah.
So, since x has to be greater than 0, x minus 1 has to be greater than or equal to 0. All we're trying to say is x minus 1 is a natural number. So we said x is the smallest thing that's not even or odd. X minus 1 is still a natural number, and it's smaller than x, therefore it is even or odd. And we're going to show that leads to x being even or odd, contradiction. X is the smallest thing that's not even or odd. X minus 1 is smaller than x, therefore it is even or odd. And we use that to show that x is even or odd, contradiction. That's a big picture of what we're doing. Let's wrap our heads around all that. So I know 0 is even. I know x is not even and x is not odd. Therefore x is not 0. Therefore x is bigger than 0. If x is bigger than 0, x minus 1 is greater than or equal to 0. You good with that? Which just gives us that x minus 1 is a natural number, right? If x is a natural number, greater than 0, then x minus 1 is a natural number. That's all we're trying to say. So x minus 1 is a natural. We'll just read it how it says it. Since x is the least element of big X, x minus 1 is not in big X. Big X was a set of all things that are not even and not odd. X minus 1 isn't in there. Therefore, x minus 1 is even or it is odd. It has to be at least one of those. Maybe it's both, who knows, but it's at least one of those, right? Well, therefore, if x minus 1 is, if x minus 1 is even, what does that mean? There exists some integer a such that x minus 1 equals 2a, which means x is equal to 2a plus 1, which means x is odd. Right? Similarly, if x minus 1 is odd, there exists a such that x minus 1 equals 2a plus 1, plus 1 to both sides, factor out the 2, therefore x is even. So if therefore x minus 1 is even or odd, and we just really showed if x minus 1 is even or odd, in either case, x is even or odd. Contradiction. What was x?
Neither.
X was the smallest natural number that was neither even nor odd. We just showed that that led to it being even or odd. Contradiction. Doesn't work. Broken worldview. You can't have x is not even or odd and x is even or odd. Right? Everyone understand the concept? Am I stressing this too hard? Should we do big picture what we did one more time?
Yeah.
Let's say big picture what we were doing one more time. So we're proving every natural number is even or odd. We're saying let x be the set of all natural numbers that aren't even and aren't odd. We assume by way of contradiction that x is not empty. We know x is empty. We assume by way of contradiction that x is not empty. Since x is a subset of natural numbers, I'm going to say big X to try and help clarify what I'm talking about the set. Since big X is a subset of natural numbers, big X has a least element, little x. That's what we're calling it. So what is little x? It is the smallest natural number that is not even and not odd. We showed that x minus 1 is still a natural number, and x minus 1 is less than x. Since x minus 1 is less than x, and x is the smallest natural that is not even and not odd, then x minus 1 has to be even or odd. And if it's even, then x was odd. If it's odd, then x was even. In either case, x is even or odd. Contradiction. This is really tough the first time you come across it, so ask any questions you have. If anything doesn't make sense, let's work with it. Or should we just keep going with more examples? Big sigh.
I say we go with more examples.
Well, since the whole class agrees with Peter, we'll continue with examples. All right. Actually, this isn't proof by contradiction. It's just a nice little extension of this proof over here so that we can start using this fact from here on out in the class. So we're going to do a quick proof now that every integer is even or odd. How's that different from what we just did over here?
Because integers include negatives.
Right. Over here we just proved naturals. Now we need to show it's true for all integers, not just the naturals. Okay. So we're going to prove that every integer is either even or odd. Let x be any integer you want, doesn't matter. Now I need to show it's either even or odd, right? Okay. We have two cases. X is greater than or equal to 0, or x is less than 0, right?
Yeah.
If x is greater than or equal to 0, then x is what?
A natural.
A natural number. And we just really showed every natural number is even or odd. We're done. Okay, what about if x is less than 0? What does that give us?
The negative x is greater than 0.
Right. If x is less than 0, negative x is greater than 0, right? You with me so far?
Yeah.
So then negative x is a natural number, right? Didn't know negatives could be natural, did you? What?
I'm genuinely confused.
I know. X is a number less than 0. X is negative. So a negative of a negative is positive.
Oh,
So a negative of a negative integer is a natural.
Okay.
With me? Okay. So we know that negative x is a natural. Therefore, we know negative x is even or odd, and we need to show in either case x is even or x is odd. Right? And then we're done? So I know
Why couldn't you just leave it?
I need to show that x is even or odd. Me saying that negative x is even or odd doesn't tell me x is even or odd. Maybe when you take the negative of an integer, it switches it from even to odd.
I think she's confused because you said in the second one that x is even or odd with the natural.
Oh, sorry. I might have said the wrong thing. So we know that negative x is even or odd. We need to use this to show that x is even or odd. Well, if negative x is even, what does that mean? That means there exists some integer a such that negative x equals 2a, which gives us x is equal to 2 times negative a, which gives us x is even. So if negative x is even, then x is even. Similarly, if negative x is odd, negative x is equal to 2a plus 1. Let's see. Multiply both sides by negative 1. Plus 1 and minus 1 from the right-hand side. So negative 1 is the same thing as negative 2 plus 1, right? Factor out a 2 from these two terms. Therefore, x is odd. Therefore, x is even or odd in either case. If x was greater than or equal to 0, we got it's even or odd. If x was less than 0, we got it was even or odd. Therefore, every integer is even or odd. Good on that? Okay, now we'll do another proof, smallest counterexample. A lot of these proofs are going to have sigma notation, so maybe quick recap on sigma notation. If I do the sum from k equals 2 to 5 of k squared minus 1, do you know what that says? Does everyone understand this notation, or should I write it out?
Right now.
Okay, so this is equal to, we plug in 2 for k, we start, this is what we start with. So plug in 2 for k, we get 2 squared minus 1 is 3. So 3. So 3 is what we get when we plug in 2 for k. Plus, now we plug in 3 for k. 3 squared minus 1 is 8. Now we plug in 4 for k. 4 squared minus 1 is 15. Now we plug in 5 for k. 5 squared minus 1 is. Now we plug in 6 for k. No, we stop when we reach 5, and we're done. That's what the sigma notation means. Right?
What do you want to do it for?
I did it for k equal to 2, k equal to 3, k equal to 4, k equal to 5. We wrote out 4 expressions. Or 4 numbers. I should say expressions, that's one expression. Good? Okay, that's sigma notation. If you have any more questions about sigma notation, or if you have lost any of the proof, let me know, because we're going to be using a lot of sigma notation now. All our proofs basically are going to use it. As you can see, sigma notation, sigma notation, sigma notation, sigma notation, sigma notation. So, lots of them. So let's do the next proof. What are we doing? We're going to prove that the sum of the first n odd numbers is equal to n squared. Right? So the sum of the first 1 odd numbers is equal to 1 squared. The sum of the first 2 odd numbers is equal to 2 squared. The sum of the first 3 odd numbers is equal to 3 squared, etc. You understand what we're trying to prove? Mm-hmm. We're trying to prove that for 1 plus 3 plus 5 plus 7 plus 9 all the way up to 2n plus 1, the nth odd number. What's the third odd number? 5. Or 2 times 3 minus 1. What's the 10th odd number?
2 times 10 minus 1.
Just 19, right? Or 2 times 10 minus 1, 19. So this gives you the nth odd number. Right? So the sum of the first n odd numbers is equal to n squared. We're proving that this is true for all n in n greater than or equal to 1. We're not including the 0 case, I guess. So for all natural numbers starting at 1, this is true. It works for 0 too, but I guess the author starts at 1. This is saying the exact same thing as this. The sum from k equals 1 to n of the kth odd number is equal to n squared. You understand? Okay, let's do the proof.
Wait, so you're proving that those two are equal?
I am proving that, now I lost it, that this equals this.
Okay.
I was just showing this written the exact same way in case you were confused by segment notation. Okay, so proof for all n greater than or equal to 1. The sum from k equals 1 to n of 2 to the k minus 1 is equal to n squared. Okay. We're going to do proof by smallest counterexample. So 1, let big X be the set of all natural numbers of all n in n such that n is greater than or equal to 1 and n makes this false. We know that this statement is true for all natural numbers greater than or equal to 1. I'm saying let X be a set of all natural numbers that make it as false. We know X is empty. Right?
Okay.
So assume by way of contradiction that what?
It's not, or it is, X is not empty.
Yeah, assume by way of contradiction that X is not equal to the empty set, big X. I'm going to start calling this A so that we don't get confused with the X. Will you be confused if I change the letter?
No.
Okay. So let me call this A and this A so that we don't get confused with the X. The author uses X, but we'll stick with A. So assume by way of contradiction that A is not the empty set. So if A is not empty, then what?
There exists something in it?
Yeah, then not only there exists something, but then by well-ordering principle, A has a least element, right?
Yeah.
Least element X. So what is X? It is the smallest natural number that makes the statement false. So every number smaller than X makes the statement true. Every natural number smaller than X makes the statement true. X is the smallest natural number that makes the statement false. So X minus 1 makes the statement true. As long as X minus 1 is greater than or equal to 1. Right? So we need to make sure that X minus 1 is what this statement talks about. So we need to make sure X minus 1 is greater than or equal to 1. So I need to show that X is not equal to 1. If X is not 1, then X has to be greater than or equal to 1, which means X minus 1 is greater than or equal to 1, which means the statement is talking about X minus 1. You with me on that?
Wait,
Okay.
you're saying X has to be greater than or equal to 1, and then you said X minus 1 is then greater than or equal to 1.
I need to show that X is greater than 1. So then I know that X minus 1 is greater than or equal to 1. So then I know that this statement has to be true for X minus 1. And then I show this statement being true for X minus 1 means it's true for X, contradiction. Because X is the smallest thing that makes that statement false. Okay. So let's see. Since the sum from k equals 1 to 1 of 2k minus 1 is equal to 1 squared, comma, then 1 is not in A, which gives us X is greater than 1, which gives us X minus 1 is greater than or equal to 1. You good with all the logic there?
Can you go over it?
Yes, I sure can. 1 makes the statement true, right?
Okay.
A is a set of all things that make the statement false. So 1's not in A. x is the smallest thing that makes a statement false. Since x can't be 1, because we know x is an A and 1's not an A, I know x now can't be 1. So what's the smallest thing x could possibly be now?
2.
2. So the smallest possible thing x minus 1 could be is 1.
Okay.
That's all we're trying to say, is that x minus 1 is greater than or equal to 1. That's all this line is trying to say. Since, I don't know if we need to say this, we'll just write it out, I guess. Since x minus 1 is less than x, then x minus 1 is not in A. How do I know that?
Because x is the smallest.
X is the smallest number.
X is the smallest thing in A. So x minus 1 is not in A. A is a set of all the things that make it false. Since x minus 1 is not in A, then x minus 1 must make it
True.
true.
Okay.
So 6. Then the sum from k equals 1 to x minus 1 of 2 to the k minus 1 is equal to x minus 1 squared. Right? X minus 1 makes the statement true. When you plug in x minus 1 for n, it's true. X minus 1 is a natural number that makes the statement true. You with me?
Mm-hmm.
Yeah.
Now, I need to use the fact that x minus 1 makes a statement true to show that x makes a statement true. How do I show that x makes that statement true? I need to show on the side I'm trying to get that the sum from k equals 1 to x of 2k minus 1 is equal to x squared. If I can show this, I've showed that the statement is true for x. Right?
Yeah, but how do you show that?
And that will be my contradiction. So I need to use this to show this. Right?
Okay.
How can I make the left-hand side of this look like the left-hand side of this?
You can add 2k plus 1 or 2x plus 1.
2x minus 1 to both sides. Right? If I take this and I add 2x minus 1 to it, I get this.
What?
Okay. Let's see. If I have the sum from k equals 1 to 4 of 2k minus 1, and I add to this 5k minus 1, or 9, then I get the sum from k equals 1 to 5 of 2k minus 1.
Okay.
1 plus 3 plus 5 plus 7 plus 9 is equal to 1 plus 3 plus 5 plus 7 plus 9. The sum of the first x minus 1 odds plus the x odd. Oh, sorry, I need to finish this to make sense. Is equal to 2 to the x minus 1 squared plus 2x minus 1. I added the x odd to both sides of this equation to get this. And turn that to that. Same way, adding the fifth odd to both sides of this, turn this into this. And here's what it did to the other side. Is anyone still lost by that? This is dense.
Yeah, I'm completely lost.
Okay.
It might help if you write it out.
How you're doing x minus 1 and then you go, with your example, you go from 4 to 5. So I don't get why that would help.
5 minus 1. 5 minus 1 is equal to, or 5 minus 1 plus 2 times 5 minus 1. I guess I don't use square brackets. Is equal to the sum from k equals 1 to 5 of 2 to the k minus 1 So let's start from the beginning. Let's start this with 2. 2, 2, 2. Something we can easily do in our head. The sum of from k equals 1 to 1. This is just, in this case, this over here is just 1, right? Plus, what's this? 3 is equal to 1 plus 3.
I'm confused because if you have 2 minus 1, is that really the same though?
2 minus 1 is what?
1.
1. What's the sum from 1 equals 1 is 2 to the k minus 1? Plug in 1 for k.
Yeah, it's just 1.
Yeah, it's just 1.
Okay, so why do you have a 3?
Oh, no, that's 2. Why do I have this 3? 2 times 2 is 4, minus 1 is 3.
You just continue with the term to make it the number up.
And then this one, you understand this one?
Yeah.
Okay, so now let's increment it. Now let's do 3. 3, 2 times, leave that at 2. 3, 3. So that becomes plus 5. This one over here is 1 plus 3, and then we just read it plus 5. In general, x, the sum of the first x minus 1 odds plus the xth odd is equal to the sum of the first x odds. So when I add 2x minus 1 to this, I get this. When I add 2x minus 1 to this, I get this. Good? It's kind of weird because we're using x for a natural number here instead of the way we're used to seeing x as being a real number. Okay. So now I need to just show that this is really x squared, right?
Yeah.
So this is equal to, let's multiply it out. This thing squared out is x squared minus 2x plus 1. Then we have plus 2x minus 1 is equal to x squared. Okay. 8. Therefore, x is not in A. Contradiction. 9. Therefore, whatever we have out there. Therefore, for all n greater than or equal to 1, the sum from k equals 1 to n of 2k minus 1 is equal to n squared. I assume you're okay with the last couple lines there. Anything weird? Next example. All right. Let's see what the next one is going to be. Show that the sum from k equals 0 to n of a to the k is equal to a to the n plus 1 minus 1 over a minus 1, where a is not 0 and a is not 1. Why do we require that a is not 1 in this equation?
If A is 1, then the denominator is 0. Which is
Yeah, this becomes 0. And then why do we say that a is not equal to 0? It's not true at 0 because all these terms would be 0, and we'd have 0 equals 1. So it's not true at 0, and 1 breaks it. So as long as a is not 0 or 1, we're good. That's what we're going to prove.
Why would you say K equals 0 then? Why not just...
K can be 0. I'm saying a can't be 0.
Okay. I see.
All right, so proof. Let a be any real number such that a is not equal to 0 and a is not equal to 1.
Any real number?
Yeah, doesn't matter what it is. A can be anything, just can't be 0 or 1. Sorry, not let, if. some real number that's not equal to 0 or 1, comma, then the sum from k equals 0 to 1 to n, let's see this one, from k equals 0 to n of a to the k is equal to a to the n plus 1 minus 1 over a minus 1. So this is true for all n in n, for every natural number. You with me? So, concrete example of what we're saying, in the case where n is 5, we're saying a to the 0 plus a to the 1 plus a to the 2 plus a to the 3. In the case where n is 3 is equal to a to the 4 minus 1 over a minus 1. That's a concrete example of one of the cases we're proving. We're proving it's true for any natural number n that you pick. In this case, we picked n to be 3. And a can be any real number you want, as long as it's not 0 or 1. So if you were to plug in 19 for a here, you'd get a true equation. If you plug in pi, you get a true equation. So we're going to prove it's true for any real number you choose, as long as it's not 0 or 1, and for all natural numbers n. Okay. 1. Let A be what? The set of all natural numbers that make the statement false. So let A be the set of all the natural numbers n such that that is false. I don't want to rewrite it. Don't be lazy like me in your homework. 2. Assume by way of contradiction that what?
It's not the empty set.
Yeah. That A is not the empty set. Assume that there is some natural number that makes this statement false. Assume that A, the set of all natural numbers that make the statement false, is empty. Or is not empty. So if A is not empty, then what? 3. And by well-ordering principle, A has what?
And the least element.
A least element. X. What do we want to do? We want to look at x minus 1. So since x is the smallest thing that makes a statement false, x minus 1 makes a statement true, as long as x minus 1 is a natural number. So we need to make sure x minus 1 is a natural number. How do we do that? We show that x isn't 0. If x isn't 0, then x has to be greater than 0, which means x minus 1 is greater than or equal to 0. Since the sum from k equals 0 to 0 of a to the k is equal to a to the 0 is equal to 1 is equal to a to the 1 minus 1 over a to the 1 minus 1, comma, then 0 is not in a, which gives us that x is greater than 0, which gives us that x minus 1 is greater than or equal to 0, which gives us x minus 1 is not, x minus 1 makes the statement true. Right? X is the smallest thing that doesn't make the statement true. X minus 1 is also greater than or equal to 0. Therefore, x minus 1 makes the statement true. You with me? Okay, if x minus 1 makes the statement true, what does that mean? That means that it's not in A, which means that the sum from k equals 0 to x minus 1 of a to the k is equal to a to the x minus 1 all over a minus 1. Right? Sorry, I forgot my then in front of that. That looks weird. Right? X minus 1 makes the statement true. When you plug in x minus 1 for n up there, you get this. Right? Now, what are we trying to show? we're trying to show that x makes the statement true, right? If x doesn't make the statement true and x makes the statement true, contradiction. What does it mean for x to make the statement true? That means that the sum from k equals 0 to n of a to x of a to the k is equal to a to the x plus 1 minus 1 all over a minus 1. If we can show this is true from this, we're done. Right? So, I'm going to take this. What am I going to add to both sides?
1.
Not 1.
They're going to add itself.
You're gonna add a
You're
k.
gonna add
A to
x,
the k.
k, x to the power of k, or a to the power of x, sorry.
I'm going to add a to the power of x to both sides. So, with this, I can write the sum, maybe we'll be real explicit, from k equals 0 to x minus 1 of a to the k plus a to the x is equal to a to the x minus 1 over a minus 1 plus a to the x. You good with that? Just add a to the x to both sides.
Why are you doing that?
Because I'm trying to get this to be a sum from k equals 0 to x of a to the k.
But why not a to the k? Like, why are you adding a to the x? I don't get that.
A to the k is a dummy variable. It starts out 0, then 1, then 2, then 3, then 4, all the way up to x minus 1.
Oh, now I get
Don't
why you're-
forget that k is a dummy variable. Yeah. So now, what is this plus this? That is the sum from k equals 0 to x of a to the k. Right?
Yep.
Is that weird to anyone? No. Okay. So that's what this is, adding ax to both sides. And now this is equal to whatever this simplifies to. Get a common denominator, so let's see, we have a to the x minus 1 plus, I'm going to multiply top and bottom of this by a minus 1. So we're going to get, maybe don't do too much math in my head in case I lose you guys. So we'll keep it really simple. Plus a to the x times a minus 1 over a minus 1. Have I cheated?
Yeah, you're cheating. Why are you again?
By 1 to get a common denominator. So this is now equal to a to the x minus 1 plus a to the x times a minus 1 all over a minus 1. For the love, please tell me that's okay.
Yes, it's okay.
5 halves plus 7 halves is equal to 12 halves. That's all I'm doing. That has the same denominator, that has the same denominator. We're just putting them all together. I like to hang out. Okay, so now distribute a to the x times a. Well, we'll write this first. So we have a to the x minus 1 plus, what's a to the x times a? What?
ax plus 1.
What is 2 to the 10 times 2 equal to? 2 to the 11. You guys, you need to go back and do just algebra. You really do.
We missed like a third of our year, so.
What does that have to do with anything? You have the internet. You need a textbook. I bet you might be able to find one in the school or in the library, or I have one. You can learn algebra. Okay. So, Rhoda, a to the x times a is?
A to the x plus 1.
Wonderful. A to the x plus 1. And a to the x times negative 1 is?
Negative.
Negative what?
Yeah.
Negative a to the x. Wonderful. Okay.
Now I have a to the x plus 1
Oh, you're going to have to divide. So let me write to the side what we're trying to make this equal to. Sorry, this is all over a minus 1. We're trying to get that this is what? A to the x plus 1 minus 1 over a minus 1. That's what we're trying to make it look like, right? Which is what we have. Negative a to the x and a to the x cancel out. Write this one before this one. So this is equal to a to the x plus 1 minus 1 all over a minus 1. Right? And now, what does that tell us? Therefore what?
Therefore,
It's true.
X is. So X is not an A.
X is not in A. Contradiction. Therefore, statement true. I want to rewrite it. Statement true. Whatever that thing is true. That is true for all natural numbers in N. Right?
Okay.
We assumed it was false, got a contradiction, therefore it's true. You feel like you could do these on your own now?
No.
Well, you're going to have to.
Holy sun.
How much time have we taken? 45 minutes? I'm going to skip the next example, do this, and then if we have time, go back to that. Just because I don't know that it's as important, and I want to make sure you guys know the Fibonacci numbers. How many of you guys have come across Fibonacci sequence before?
I don't even know what that means.
Few of you? Alright. The Fibonacci sequence, or the Fibonacci numbers, or let's see, what do we call it in this class? The Fibonacci numbers. The Fibonacci numbers are the list of numbers f0, f1, f2, where f0 is equal to 1, f1 is equal to 1, and then from there on out, f of n is equal to the sum of the two previous numbers. So, the first two numbers are 1, and then every term after that is the sum of the previous two numbers. So what's the next term?
2.
2. What comes after 2?
3.
Good job. What comes after 3? Not that. 3. After 3 comes 5. Then
44.
no.
34.
Yeah. Then
55.
55. Then
89.
Infinity.
What's the biggest one?
There is
Okay, there is a 1.
Infinity is big.
Infinity is not a natural number. It's not even a real number.
So,
It's what we call an extended real number, which I don't think the Fibonacci sequence has that as its codomain. Highly unlikely. Anyways, so there's the Fibonacci numbers. That's what we mean by Fibonacci numbers. Okay, now we're going to do a proof with them. We're going to prove that the nth Fibonacci number is always less than or equal to 1.7 to the n.
what?
Okay, why?
Why 1.9?
I don't care.
Because it didn't work with 1.6. You don't care? You don't think that's pretty crazy?
That's weird. Wait,
I say, what's the 1000th Fibonacci number? We say, I don't know, but it's less than 1.7 to the 1000.
Wow, amazing.
That is amazing. How else would you know it's bounded like that? And knowing how numbers are bounded is very useful. Ask Emma. We have to use the fact that certain sequences of numbers are bounded in ways all the time. Because we could use something like that to start calculating the limit of the thing. Well, in this case, it's going to blow up. But if we were looking at a ratio of it, might find ratios that converge. Never mind. That's not converge. Forget everything I said. It can be very useful and very interesting. All right, so let's do this proof. Proof that for all n in n, the nth Fibonacci number is less than or equal to 1.7.
1.7 to the n, right?
Oh, yeah. Okay, so 1. How am I going to start this?
By way
Come
of
on,
contradiction.
you can do this. What? Let
X,
A,
A,
B.
equal.
where you only need one letter.
What?
You said B.
Now do.
And in the
And
natural
in the
numbers.
The set of all natural numbers
dot dot.
such that
Fn
That's
is
false.
greater than 1.7 power of
Fn is greater than, not equal, greater than 1.7 to the n.
Wow. Being a number three.
Yeah, amazing. Next line, 2.
By way of contradiction.
Assume by way of contradiction. By way of contradiction, that what?
That A is not being set.
That A is not empty. Then what? By.
Then by way of well ordering principle.
Then by well ordering principle,
A has at least element X.
A has at least element X. Then what?
Now this is your turn.
We need to show, so we know the statement's false for X, we need it to be true for X minus 1. How can we make it true for X minus 1?
Wait, what do we want to be true for x minus 1?
The statement. We want X minus 1 in A, or not in A. We want X minus 1 to be a natural number that makes the statement true.
Okay.
So how can I make sure X minus 1 is a natural?
Make sure that x is greater than 0.
Make sure X is greater than 0. How can I show that X is greater than 0?
Doesn't it have to be greater than 1? No.
Observe that 1.7
Actually-
is 0.
Has to be greater than 1.
Yeah, we need to show that X minus 1 and X minus 2 are both natural numbers because f of n is going to be the sum of the two previous numbers. So observe that f sub 1 is less than or equal to 1 to the 1, comma, and, well, f sub 2 is less than or equal to 1.7, sorry, 1.7 to the 1. And maybe write out what they actually equal in case you're getting lost. So f sub 1, what does that equal? 1, which is definitely less than or equal to 1.7 to the 1. And f sub 2 is equal to 1 is definitely less than or equal to 1.7 squared. Right? Observe that and that, comma. So x is greater than or equal to what?
F to the 2
3.
equal 1? Because look at the sequence. 1, 1.
The first two Fibonacci numbers are 1. F of 1, F of 2, F of 3, F of 4, F of 5, F of 6, F of 7, F of 8, F of 9, etc.
Now, why did you...
Yeah, why did you do F to the 1, F to the 2? Isn't it F to the 0 and F to the 1?
I started with a 1, but I said this for all naturals. And we have an F sub 0 there, F sub 0. Yes, you are right.
Wait.
Thank you. So F sub 0 is equal to that. F sub 1 is equal to that. So this is F sub 0, this is F sub 1, this is F sub 2,
Why
3,
does
4,
it
5.
start like that?
Huh?
Why does it start at 0?
Because we said F of 0 equals 1.
Huh?
And we said F of 1 equals 1, and then from there on out, it's just the sum of the two previous terms. So x is greater than or equal to 2, which gives us x minus 1 and
Wait, now I'm confused. Why do we have 1.7 power 2?
We should have 1.7 power
0 to the 1.
I'm sorry.
No, that's good. Make sure everything's right. All my ends need to match up.
I'm confused.
So x is greater than or equal to 2 tells us that x minus 1 and x minus 2 are natural numbers. Right?
Yeah.
Okay, Why does that make x greater than or equal to 2?
X can't be 1,
It says
or X can't be 0, and X can't be 1, because those make the statement true. So the smallest X can be is 2. X is the smallest thing that makes the statement false.
Oh.
F of 0 makes it true. F of 1 makes it true.
Okay.
So the smallest thing that could possibly make it false so far is F of 2. So the smallest thing X can be so far is 2. Right?
Okay, x is the least element, and you're saying the smallest thing x. Like, why didn't you just say x is equal to 2? It's the least element.
It's the least element that makes the statement false. We don't know the smallest thing that makes the statement false. We know for sure 1 makes a statement, or 0 makes a statement true, and 1 makes a statement true. Therefore, it can't be 0 and it can't be 1.
So we know
It might be 2,
or greater.
but it could still be greater than. It's just the smallest thing that makes the statement false.
I see.
Now, there is nothing that makes a statement false, so it definitely can't be 2. But, yeah. So now we know that x minus 1 and x minus 2 are naturals, which means x minus 1 and x minus 2 make the statement true, right?
Yes.
Then, f of n minus 2, we know, is less than or equal to 1.7 to the n minus 2. And f to the n minus 1, oops, those are supposed to be x's, not n's. X is less than or equal to 1.7 to the x minus 1. Right? X minus 1 and x minus 2 are natural numbers, and they're smaller than the smallest thing that makes the statement false. Therefore, they make the statement true. What does it mean for x minus 2 to make the statement true? It means that this is true. What does it mean for x minus 1 to make the statement true? It means this is true. With me? Now we're trying to use that to show, ultimately, where are we trying to get? We're trying to get that f sub x is less than or equal to 1.7 to the x. That's what we're trying to show.
So we're trying to show that the least element makes it true.
Yes.
Okay.
That's exactly what we're trying to show. Looks like I slanted a lot. And f sub x minus 1 is less than or equal to 1.7 to the x minus 1. Okay. Then, what does f sub x equal?
F sub x minus 2 plus f sub x minus 1.
Perfect. F sub x minus 1 plus f sub x minus 2, which we know is less than or equal to the sum of these two numbers, 1.7 to the x minus 1 plus 1.7 to the x minus 2. You with me so far? Anyone lost with anything I have written so far? Because from here on out, it's just algebra. We know that this number is less than or equal to this number, and this number is less than or equal to this number. So the sum of these two is less than or equal to the sum of these two. And f sub x is, by definition, the sum of these two. That's what the Fibonacci sequence is. The nth term is equal to, where do I have it written? The nth term is equal to f of n minus 1 plus f of n minus 2. The xth term is equal to f of x minus 1 plus f of x minus 2. Everyone good? Okay, now for the algebra. Why do I keep slanting down again? Plus 1.7 to the x minus 1. Okay,
X
X
minus 2.
x minus 2, thank you. Okay, but this, that is just equal to, I'm going to factor out a 1.7 to the x minus 2 from both those. So 1.7 to the x minus 2, we don't need parentheses, 1.7 to the x minus 2 times, when I factor it out of this, what am I left with?
1.7.
1.7.
What? How do you do that?
Okay. Let's plug in numbers. If I have 1.7 to to the 3 plus 1.7 to the 2. And I want to factor out a 1.7 squared. That's the same thing as 1.7 squared times 1.7 plus 1.
What?
What is 1.7 cubed? That's 1.7 3 times. 1, 2, 3. Okay, we got it all.
And why the plus
1.7 squared times 1 is equal to?
Okay, my question is though, how do you factor it from 1.7 from x minus 1?
I took x minus 2 from this, leaving 1. I took x minus 2 from this, or leaving 1.7, and I took it from that, leaving this. It's the exact same thing. Going from this to this is exactly what we're doing, going from this to this. Right? We good now? It's just exponents. Are we good? That's a
I
big
think
nod.
the biggest thing that's going to be a struggle for us is doing the algebra part.
Yeah, that's why you were supposed to learn algebra before you took this class. Maybe we'll do algebra over the summer.
I'm down.
We're already doing Western rules.
We haven't decided yet.
I decided.
It will depend on what my students are come that point. So most of you probably won't even have to say.
Don't pretend like you didn't cancel class last weekend.
I did. Okay, so this is equal to, add these two together, we have 1.7 times x minus 2, and 1.7 plus 1 is
2.7.
2.7. And this is less than or equal to, what's 1.7 squared?
1.
What's 17 squared? 289, so 1.7 squared is 2.89. Ah, we made it bigger. So that's equal to 1.7 x to the minus 2 times 1.7 squared is equal to 1.7 to the x.
Wait, why are you squaring it?
I'm just rewriting this number a different way so you can see I'm going to add exponents.
I know, why'd you write that number in the first place?
What number?
2.89.
I'm just replacing this with a bigger number. I made it bigger,
Oh.
so my inequality is still true.
Okay.
Wait.
Okay.
Oh, okay.
Okay.
So you're just simply trying to make so that the inequality would be true.
I'm simply trying to show that f of x is less than or equal to 1.7 to the x. So f of x is equal to, is less than or equal to, is equal to, is equal to, is less than or equal to 1.7 to the x. Right?
Okay.
Therefore, x is not in a contradiction, therefore the statement's true.
I don't know how you expect us to do this.
The same way past students have done it, the same way I did it. I strongly recommend you read these sections in the book because this way of proving is, students always struggle with it.
Yeah, but the guy talks funny.
He does have a weird voice.
Did you say he talks funny?
Gotta learn to read a textbook. All right. We'll leave it for there, and we'll move on to induction. Rhoda stole my spot. Kids these days. All right. Hopefully that doesn't look proper. Okay. So that's proof by smallest counterexample. Now we're going to do proof by induction. Good news about proof by induction. You can always just use proof by smallest counterexample, and you never have to use proof by induction.
Wow.
However, proof by induction is way easier,
Okay, great.
I think. Everyone uses proof by induction. You'll see this in basically every math class you do. You'll hardly see this.
Great.
Yes. Okay. So proof by induction, principle of induction. It's fairly intuitive. Imagine I have some secret set over here. We're going to call it S. and you're trying to guess everything in S that you can, and I give you 2 hints. I tell you that 0 is in S, and I tell you anytime K is in S, then we know that K plus 1 is also in S. So what do you know is in S? Tell me everything you can that's in S.
All the
All
natural
natural
numbers.
numbers.
You know what?
All the naturals.
numbers.
How did you come to that?
Because there's 0 and then if K.
Oh, but K can equal like
Oh,
negative
K
1.
could equal any.
K has to be in S though. So what do I know for sure is in here? I know that 0's in here, right?
And 1 and 2.
And 1.
How do I know 1's in there?
Because
K
K
can
will
be
be
K can
0.
equal 0.
Oh, so 1's in there. Okay, but that's it.
No.
Oh no, there's 2's also in there. And
That's-
3, and 4, and yes, exactly what you said before. It is equal to the set of all natural numbers. That is the principle of induction.
No, wait, why can't you
Yeah,
say
why
it's
can't
in
you have
negatives?
negatives?
Show me a negative in there.
Well, can't you say K is -3?
If K is in, if negative 3 is in there, then I know negative 2 is in there. But is negative 3 in there? Nope.
But it could be.
K has
If
to
the
be in S.
only hints that you gave us with those, then that.
Right. What are all the things you know are for sure in there?
0.
You know for sure 0's in there. And you know for sure 1's in there. And you know for sure 2's in there. And you know for sure 3's in there. So you know for sure that all the natural numbers are in there. I shouldn't say it's equal to naturals, but you know for sure all the naturals are in there, right?
So the natural.
So now what if I told you S has this property, and I told you that S is a subset of the naturals?
So I didn't see any of those.
You said this means S has all the naturals, right?
Yeah.
And this means all of S is in the naturals. They're subsets of each other, therefore they're equal. Right? When you said all the naturals were in here, that's the same thing as saying the naturals are a subset of S. So if I tell you this, then you know the naturals are a subset of the set. And if I tell you this, then you know that the set is a subset of the naturals, therefore they're equal.
Right.
Okay, that's exactly what the principle of induction says. Let A be a set of natural numbers. If 0 is in A, and if K being in A implies K plus 1 is in A, then A is equal to all the naturals. Easy as pie, right? Huh?
Well, it doesn't, it says that the naturals are a subset of A, but it doesn't say that A is a subset of the naturals.
This being true, 0 being in A, and K being in A implying K plus 1 is in A, implies the naturals are a subset of A.
Yeah.
This top line says A is a subset of naturals.
Oh.
Therefore, they're equal. Now we're going to prove it. Guess what we're going to use to prove it?
That.
Yeah, we're going to do a proof by smallest counterexample.
Oh, wait, we're gonna prove that the principle of induction works with proof by smallest counterexample.
Yes.
Okay, that makes more sense, because in our calculus class, we proved the principle of induction using the proof by induction.
No, we didn't do a proof by induction calculus. We did a,
What did we do?
to do a proof by induction, we had a definition of what it meant to be. We went about this quite differently because we had a definition of what an inductive set was.
Oh, that probably explains that.
And we defined the natural numbers to be the intersection of every inductive set.
Okay.
Yeah, it was different. We didn't come at it this way. I think that this is a more intuitive way to come at it. But in calculus, we got to get up and going. We don't have time to spend a whole class dedicated to this kind of stuff. Anyways. Okay, so let's do proof that proof by induction works. So I'm going to prove the principle of induction. Let A be a set of natural numbers such that 0 is in A, not 1, sorry. Such that 0 is in A, and such that if K is in A, K plus 1 is in A. Right?
Uh-huh.
Just exactly what we said over here.
Well, I thought you had to change it.
What?
So you have to make it not true.
I'm going to do a proof by induction, or we're going to assume, we'll do what you're saying. Stick with me. Okay, let A be the set of all natural numbers and make the statement true. Or, sorry, that satisfies. let A be the set of natural numbers such that 0 is in A, and anytime K is in A, K plus 1 is in A. I'm trying to show that A is equal to the natural numbers. Right? I'm going to let X be the set of all the natural numbers that aren't in A. And assume by way of contradiction that X is not empty. If A is not equal to all the natural numbers, then that means when you take their subtraction, you get something. So I know in my head A is all the natural numbers. So all the natural numbers minus all the natural numbers is the empty set. Assume by way of contradiction that it's not the empty set. You with me? Okay. So, by the well-ordered principle, big X has some least element, little x. Since 0 is in A is given, I know that what? X has to be bigger than A, or bigger than 0. Right? Little x is the smallest natural number not in A. Right? I know that 0 is in A. X is not in A. X is the smallest thing not in A, so x has to be bigger than 0, which means x minus 1 has to be a natural. You with me so far?
Okay.
So x minus 1, where was I? So x minus 1 is a natural, and since x minus 1 is not in X, and x minus 1 is a natural, then x minus 1 must be in A.
Wait, can you say that again?
X is the set of all natural numbers not in A.
Yes.
Big X. Big X is a set of all natural numbers not in A. Little x is the smallest thing in big X. X minus 1 is smaller than little x. Therefore, x minus 1 is in A. Big X was everything not in A.
Okay.
Little x was the smallest thing in big X. X minus 1 is smaller than little x. Therefore, x minus 1 is in A.
Okay.
You follow all that?
Yeah.
Okay. So then x minus 1 is in A. But wait a second. If x minus 1 is in A, what else is in A?
X minus 1 plus 1.
X minus 1 plus 1. Remember, if k is in A, then k plus 1 has to be in A, which gives us x is in A. Contradiction.
It looks so complex, but it's actually so simple.
No.
It's
It
relatively.
looks so complex, and it is complex.
Okay, so let's do some proofs by induction. We're going to use the principle of induction. Proof. So what do I need to show that a set is all natural numbers? I need to take a subset of natural numbers. If I can show that 0 is in there, and if I can show that anytime k is in there, k plus 1 is in there, I've shown that subset of natural numbers is actually all the natural numbers. Right?
Okay.
So that's what we're going to do. So proof, which one are we going to prove? We're going to prove that the sum from k equals 0 to n of k squared is equal to 2n plus 1 times n plus 1 times n all over 6. We're going to prove that this is true for all natural numbers. 1. Let A be the set of all n in big N such that that is true.
Wait,
We're not doing a proof by contradiction anymore. We're just proving directly that A is all natural numbers. So A is the set of all the natural numbers that make the statement true. I'm going to show that 0 is in A, and I'm going to show that if k is in A, k plus 1 is in A, therefore A is all natural numbers. Notice by definition, A is a subset of natural numbers. A is all the natural numbers that satisfy some condition. So A is a subset of natural numbers. I'm going to show that 0 is in A. I'm going to show that if k is in A, k plus 1 is in A. Therefore, A is all the natural numbers. Therefore, all the natural numbers make the statement true. That's big picture what we're doing. Different from what we did over here. We would set up A to be the set of all the things that made it false. and assume, by way of contradiction, that it wasn't empty. Here, A is going to be the set of all things that make it true, and we're going to show that every natural number is in there. With me? And it's straightforward how we do it. We just need to show zeros in A, and we need to show k's in A, k plus 1's in A. Then all the natural numbers are in there. Easy as pie is what it is. Right?
Hey, we're making pie tomorrow, we'll see.
Okay. 2. How do I show that zero's in there?
It says it, it says it.
Observe that the sum from k equals 0 to 0 of k squared is equal to 0 is equal to 2 times 0
Wait, isn't that
is equal to 1 times 1 times 0 over 6. Okay.
0 to the 0 is
0 to the 0.
0 squared.
0 to the 0 is not defined. Your calculator will say it's 1 and it shouldn't. 0 to the 0 is undefined. We don't do 0 to the 0.
Why not?
It's undefined.
Why?
Because I can make it equal to multiple things. So, we're not going to get sidetracked on that. Oh, that's probably why on this one we couldn't have a 0. A can't be 0 because we're going to have a 0 to 0. Ah, that's another reason. I still think when you plug in zeros, you get no, because 0 to 0 would be 1 if you want. Never mind. Anyway, 0 to 0, undefined. Okay. So when I plug in 0 for n, I get this, right?
Yeah.
Which is true. I get this is equal to 0 is equal to 0. So that gives me that 0 is in A. We call that the base case.
Okay.
So typically when we do this one, when we show that 0's in A, we typically, instead of observe, we do base case to let you know that's what we're doing. Base case. That's equal to that gives me 0's in A. 3.
Base case. Why did you say that?
Well, you'll get comfortable with it as we do more. Let's leave it for now and just do the proof to try and give you a proof by induction. Okay, so now I've shown that 0's in A. Now I need to show k in A implies k plus 1's in A. I need to prove this. How do we prove an implication?
You assumed first.
Assume the antecedent and show that implies a conclusion. Assume k is in A. Then what? What does it mean for k to be in A?
And k plus 1.
Oh, let's not use k because we use k here. What should we use? I really don't like x, but that's what the author keeps using. All right, assume x is in A. So if x is in A, what does that mean? That means the sum from k equals 0 to x of k squared is equal to 2x plus 1 times x plus 1 times x all over 6. Right?
Why 6?
Yeah.
I know. She's great.
Okay. So now we need to show that when x is in A, that implies x plus 1 is in A. So I need to use this information to show x plus 1 is in A. How do I show x plus 1 is in A? I need to show that the sum from k equals 0 to x plus 1 of k squared is equal to, when we plug in x plus 1 to that, we get 2x plus 3 times x plus 2 times x plus 1 all over 6. Right? That's what you get when you plug in x plus 1 for n. So I need to use this to show that this is true. So first off, I want this to look like this, what do I need to add to this to get this?
What? Say that again.
How can I make this look like this? What am I missing?
A curve.
X plus 1 squared. We have the sum of all the squares from 0 to x. We need the sum of all the squares from 0 to x plus 1. All we're missing is x plus 1 squared. Right? Yeah. That adds up. So then, maybe I'll do it in line 5. Then, when we add x plus 1 squared to both sides, I get the sum from k equals 0 to x plus 1 of k squared is equal to 2x plus 1 times x plus 1 times x over 6 plus x plus 1 squared. Right?
Why x plus 1 squared? Why not just x plus 1? Oh.
Okay.
Okay, but isn't x plus 1 equal to that, not this?
All I did was took this and added x plus 1 squared to both sides. Right? And now all I need to do is show that this is actually the same thing as this, and we're done.
Oh, okay, so, okay.
Right? Okay, so I'm going to multiply top and bottom of this number by 6. So that's going to give me 2x plus 1 times x plus 1 times x plus 1 squared, or plus 6x plus 1 squared, all over 6. You good with that? I just multiply this top and bottom by 6 and row everything over 6.
Okay.
No magic, except the last part. There's no magic. Okay, now I'm going to factor an x plus 1 out of both these terms. It's going to get crazy.
Yeah.
Alright, so we're going to have x plus 1. When I factor x plus 1 out of this term, I'm just left with, on this one, I'm left with 2x plus 1 times x. And when I factor x plus 1 out of this term, I'm left with 6 times x plus 1. And this is all over 6. Right?
Okay.
Just factor out x plus 1. Anything weird? Anything magic? Anything crazy? Ready for the next step? Is that a yes?
Yeah.
Yep.
There it is. Okay, so now we're just going to simplify what's inside the square brackets. So we still have the x plus 1 on the outside. There it is. I'm just going to write my 6 over here and write this time so I don't have to worry about it. Now just everything inside the square bracket. What's 2x times x?
2x squared.
2x squared plus what's x times 1?
X.
Oh, Peter was ready. All right, what's 6 times x?
6x.
And then what's 6 times 1? Boom. You guys are going pro. All right. Next, this is equal to, rewrite my x plus 1 over 6, just get it out of the way. Okay. Now, 6x plus x is just 7x, right? Maybe we'll waste some time and write it all out again with the 7x. 2x squared plus 7x plus 6. And this is now all equal to x plus 1. We're going to factor that thing, and it's all going to be over 6. Okay, we need to factor this. Well, I've got a 2x, so one of these has to be a 2x, and the other one just has to be an x. Whatever numbers go here have to, when you multiply them, give me 6, right? And I need 2 times this one plus 1 times this one to give me 7. Right? So my numbers that give me 6, and obviously we're going to try 2 and 3. The only question is, where do I want the 3 and where do I want the 2? If I put the 3 here and the 2 here, we're going to end up with 8 x's. That's bad. So let's put the 2 or the 3 here and the 2 here. So 2 times 3 is 6. 2 times 2x is 4x, and 3 times x is 3x, giving us 7x, and then x times 2x is 2x squared. There we go. So that gives us x plus 1 is an 8. And then that gives us a is equal to n. 6. Therefore, a is equal to n. And we're done. Statement is true for all natural numbers. Doesn't get easier than that.
I think I'm more scared of the algebra than the actual proof.
You just should be. You should be terrified of the algebra. It's going to get you. Because this is as easy as proof by induction gets. We're going to come up with some cool ones for you to do. Don't worry. Okay, let's do another one. Why not? Huh? Did you say your brain's dying?
Yes.
Should we just, I guess we can do a break. We've covered all the new material, so now it's just a matter of you going over as many examples as you want.
Okay.
Because it was just, do you know how to do proof by small counterexample and proof by induction? So go ahead, go on break. When you come back, we'll just keep going through examples, and then when you're sick of that, you're sick of that, and you can start your homework. Next week we have a test. Your test on this next week.
Do you have our test
Yeah, it's a
tomorrow?
week after next week, right?
I have your tests. Are they graded? No.
So there's only 3 sections in this one?
I don't know. I know that we're done.
Okay.
There's 2 seconds.
Well, there could be sections that we're
Or
skipping.
I see you.
So yeah, go on. Come on, get out of here. Go get some air. Can't you see I don't want you anymore?
Yeah, so we should just
How's
go,
it like you?
go home, take a nap, refresh.